Let's start. Number 20. The radiation problem in deep space is something most people don't understand until you look at the actual numbers. Between Earth and Mars, there is no magnetic field to protect you. Earth's magnetic field is like an invisible shield that deflects charged particles from the sun and cosmic rays from deep space. Once you leave that protection, you're exposed to radiation levels that are fundamentally incompatible with human survival over long periods. NASA's own data from the Mars Science Laboratory mission showed that astronauts on a round trip to Mars would be exposed to roughly 662 millisieverts of radiation. To put that in perspective, that's equivalent to getting a full-body CT scan every 5 or 6 days for months on end. The annual limit for radiation workers on Earth is 50 millisieverts. A trip to Mars would expose you to more than 13 times that amount. This isn't like getting an X-ray at the dentist. We're talking about high-energy particles that punch through spacecraft walls, through spacesuits, through your body, and damage DNA at the molecular level. They cause double-strand breaks in your DNA that your cells can't always repair correctly. This leads to cancer, yes, but also something worse in the short term, which is acute radiation syndrome affecting your central nervous system, your cardiovascular system, your immune system. Studies on mice exposed to the type of radiation you'd encounter in deep space showed permanent cognitive damage. Memory formation was impaired. Decision-making capability decreased. These mice essentially got dumber, and the effects didn't reverse after the radiation exposure ended. Now imagine you're 7 months into your journey to Mars, and you need to make split-second decisions to keep yourself alive, but your brain isn't working the way it used to. Solar particle events make this even worse. These are massive eruptions from the sun that send waves of deadly radiation through space. They're unpredictable. During the Apollo missions, astronauts were lucky. If a major solar particle event had occurred while they were on the moon, they would have received a lethal dose of radiation. The mission would have ended with dead astronauts. A trip to Mars takes at least 7 months one way. The probability of encountering a major solar particle event during a 2 to 3 year mission, including time on Mars, is extremely high. You can't just hide from it either. The amount of shielding you'd need to protect against solar particle events would make the spacecraft so heavy it couldn't launch. Some people suggest using water or hydrogen as shielding, surrounding the crew compartment with tanks of water. The problem is, you'd need several meters of water in all directions to provide adequate protection. That's hundreds of tons of additional mass. The Falcon Heavy, one of the most powerful rockets currently in operation, can send about 16 tons to Mars. You'd need dozens of launches just to send the shielding, let alone the actual spacecraft, the fuel, the supplies, the crew. Even if you somehow got all that shielding to Mars, you'd face the same problem on the surface. Mars has no magnetic field and an atmosphere that's 1% as thick as Earth's. You're still getting bombarded by radiation on the surface. You'd need to live underground or build habitats with meters of regolith piled on top. Every single time you went outside, you'd be shortening your lifespan. Number 19. Bone density loss in zero gravity is not something you can exercise your way out of. Astronauts on the International Space Station lose 1 to 2% of their bone mass every month they're in space. That might not sound like much until you do the math. A 7-month trip to Mars means you'd lose 7 to 14% of your bone mass before you even arrived. Then you'd spend a year and a half on Mars, where gravity is only 38% of Earth's. Your bones would continue to deteriorate, just more slowly. By the time you got back to Earth, you'd have the bone density of an 80-year-old. Your risk of fractures would be catastrophic. We've studied this extensively on the ISS. Astronauts exercise 2 hours every day with resistance equipment specifically designed to load their bones and muscles. They still lose bone mass. They still lose muscle mass. Exercise helps, but it doesn't solve the problem. It just slows the decline. The longest anyone has spent in space continuously is 437 days. That was Valery Polyakov on the Mir space station back in 1994. In 1995, when he returned to Earth, he could barely walk. He needed months of rehabilitation, and that was after spending time in low Earth orbit, where Earth's magnetic field still provided some radiation protection, and where resupply missions could bring fresh food and equipment every few months. A Mars mission would be 2 to 3 years with no possibility of resupply, no possibility of emergency return, and radiation exposure far worse than anything experienced on Mir or the ISS. The bone loss isn't just about density. The microarchitecture of your bones changes. The trabecular bone, the spongy interior part, deteriorates faster than the cortical bone, the hard outer shell. This makes your bones not just weaker, but more brittle. They don't just break more easily, they shatter. Astronauts who've spent 6 months on the ISS take years to recover their bone density, and some never fully recover. Now imagine tripling or quadrupling that duration. You'd be looking at permanent skeletal damage, hip fractures, vertebral compression fractures. These aren't minor injuries, they're life-altering disabilities. And here's the thing nobody talks about. Once you're on Mars, you can't just come home if something goes wrong. If an astronaut on the ISS breaks a bone, they can be back on Earth in 3 hours. If you break a bone on Mars, you're stuck there for a year and a half waiting for the planets to align for a return window. You'd better hope your medical officer knows how to perform surgery in a habitat made of fabric and aluminum. Number 18. The human cardiovascular system was designed by evolution to work in 1 g of gravity. Your heart pumps blood up to your brain against gravity. The valves in your veins prevent blood from pooling in your legs. In 0 gravity, this system goes haywire. Blood shifts toward your head. Your face puffs up. Your legs get skinnier. Your heart doesn't have to work as hard to pump blood, so it gets weaker. This isn't speculation. This is observed fact from decades of spaceflight data. The heart muscle atrophies in space, just like skeletal muscle does. Astronauts return from 6-month missions on the ISS with hearts that are measurably smaller and weaker. They experience orthostatic intolerance, which means when they stand up after returning to Earth, their blood pressure drops and they pass out. This improves over time, but again, we're talking about 6-month missions. A Mars mission would be 4 to 6 times longer. Studies of astronauts' cardiovascular systems after long-duration spaceflight show concerning changes in the structure of the heart. The left ventricle, which does most of the work pumping blood through your body, becomes more spherical and less efficient. The walls get thinner. The ejection fraction, which is the percentage of blood your heart pumps out with each beat, decreases. These changes have been documented even in young, healthy astronauts who were in peak physical condition before their missions. Now imagine you're 55 years old, which is not uncommon for astronauts, and you spend 2.5 years in space and reduced gravity. Your cardiovascular system would be so deconditioned that returning to Earth's gravity might trigger heart failure. Even if you survive the return, you'd need months or years of rehabilitation. And that's assuming everything else goes right. Which brings us to another problem. The fluid shift in 0 gravity increases intracranial pressure. Several astronauts have developed vision problems in space because of this. The optic nerve swells. The eyeball changes shape. Some astronauts have come back from the ISS with permanent vision damage. They need reading glasses when they didn't before. Some have reported seeing flashing lights, which are cosmic rays hitting their retinas. These are just inconveniences. These are signs of serious physiological changes that we don't fully understand and can't fully mitigate with current technology. NASA calls this VIP, visual impairment and intracranial pressure syndrome. They don't know exactly what causes it or how to prevent it. They just know it happens and it's worse on longer missions. Number 17. The psychological challenges of a Mars mission would break most people. And, I mean that literally. You'd be locked in a tin can with 5 or 6 other people for 2 to 3 years with no privacy, no fresh air, no ability to walk away from a conflict. You couldn't open a window. You couldn't go outside without a spacesuit. Every single day would be exactly like the one before. The isolation would be crushing. Antarctica research stations offer the closest analog we have to a Mars mission. And even there, with the ability to evacuate people in emergencies, psychological problems are common. Depression, anxiety, interpersonal conflicts that escalate to violence. These happen even though people at Antarctic stations can call home whenever they want, can access the internet, can look forward to leaving in a few months. On a Mars mission, communication with Earth would have a time delay of up to 24 minutes one way, depending on where the planets are in their orbits. You couldn't have a real-time conversation with anyone back home. If you had a crisis, you couldn't call for help. You'd be truly alone in a way that no human has ever been alone before. The confined environment would amplify every annoyance. Someone's chewing would drive you insane. The sound of someone's breathing while they sleep would keep you awake at night. Personality conflicts that would be minor on Earth become major crises when you can't get away from each other. We've seen this in simulated Mars missions. HICS, the Hawaii Space Exploration Analog and Simulation, isolated crews for up to a year in a habitat on the slopes of Mauna Loa. Even in those simulations, on Earth, with the knowledge that they could walk out the door in an emergency, psychological problems emerged. Crew members developed depression. Some stopped speaking to each other. The selection process for these simulations was rigorous. These were people who wanted to be there, who had been psychologically screened. It didn't matter. The environment broke them down anyway. Now imagine the real thing. Imagine knowing that if you have a psychological breakdown, there's no emergency exit. You can't tap out. You're committed for the full duration. The suicide risk alone would be significant. How do you prevent someone from sabotaging the mission if they decide they can't take it anymore? You can't exactly restrain them for 2 years. You can't send them home. Some researchers have proposed using psychiatric medications to manage mood and anxiety during long-duration missions. That creates its own problems. These medications have side effects. They interact with the body differently in microgravity. And what happens if someone decides to stop taking their medication? What if the supply runs out? You can't exactly call in a prescription refill from Mars. Number 16. The cosmic ray problem is worse than the solar radiation problem because you can't predict cosmic rays and you can't shield against them effectively. These are high-energy particles, mostly protons and atomic nuclei, that have been accelerated to nearly the speed of light by supernova explosions. Other violent events in the galaxy. When one of these particles hits your spacecraft, it doesn't just pass through. It creates a shower of secondary particles. It can hit an aluminum wall and produce neutrons, which are even harder to shield against than the original cosmic ray. These particles damage DNA, yes, but they also damage electronics. A cosmic ray passing through a computer chip can flip bits, changing ones to zeros and zeros to ones. This causes software errors, hardware failures. The Mars rovers have experienced this. They've had to reboot their computers multiple times because of radiation-induced errors. Now, imagine that happening to the life support system of your spacecraft. Imagine a cosmic ray flipping a bit in the software that controls your oxygen production, and suddenly your oxygen levels start dropping, and you don't know why. Avionics on the spacecraft would need multiple redundant systems, each one shielded as much as possible, and even then, you'd have failures. The Apollo guidance computer had less computing power than a modern smartphone, but it was relatively immune to radiation because it used magnetic core memory, a technology we don't use anymore because it's bulky and slow. Modern computers use transistors that are nanometers across. A single cosmic ray can knock out multiple transistors. We can harden electronics against radiation to some degree, but it makes them heavier, more expensive, and less powerful. The computers on a Mars spacecraft would be years behind the current technology just because of the need for radiation hardening, and you'd still have failures. You'd still have systems going down at random times. The crew would need to be able to diagnose and repair complex electronic systems with limited tools and spare parts. They'd need to be electrical engineers, computer scientists, and mechanics all at once. The training required for a Mars crew is absurd. Each person would need to be an expert in multiple fields, because you can't bring specialists for everything. You need people who can do surgery, repair life support systems, fix the reactor if you're using nuclear power, grow food, conduct scientific experiments, maintain the spacecraft, and stay psychologically stable all at the same time. These people don't exist. Even if they did, even if you found 6 superhuman individuals who had all these skills, the cosmic ray problem would still put them at risk every single day of the mission. Number 15. The fuel requirements for a Mars mission make the whole thing borderline impossible with chemical rockets. Let's talk numbers. To get from Earth to Mars, you need to accelerate your spacecraft to about 11 kilometers per second to escape Earth's gravity. Then adjust your trajectory for the transfer to Mars. That requires a huge amount of fuel, but that's just the outbound journey. You also need fuel to slow down when you get to Mars, fuel to take off from Mars, and fuel to get back to Earth. Every kilogram of payload you want to deliver to Mars requires multiple kilograms of fuel. The rocket equation is exponential. If you want to bring more fuel, you need more fuel to carry that fuel, which means you need even more fuel to carry that fuel. The SpaceX Starship is designed to address this by refueling in orbit. The idea is you launch the Starship to low Earth orbit, then launch multiple tanker Starships to refuel it before it heads to Mars. Elon Musk has said it might take 8 to 10 refueling launches. That's 8 to 10 Starship launches just to refuel one Mars-bound Starship. Each of those launches costs money. Each of those launches has a risk of failure. If one tanker launch fails, the whole mission might be scrubbed. And that's just to get to Mars. You need to produce fuel on Mars to come back. The plan is to use in situ resource utilization, ISRU, which means making methane and oxygen from the Martian atmosphere. The atmosphere on Mars is 95% carbon dioxide. You can combine that with hydrogen to make methane, and water through the Sabatier reaction, then electrolyze the water to get oxygen and more hydrogen. This is theoretically possible, but it's never been done on Mars. It requires bringing all the equipment to Mars, setting it up, and running it for months to produce enough fuel for the return trip. If anything breaks, if the reactor fails, if a pump gives out, you're stuck on Mars forever. There's no plan B. You can't AAA. And here's the thing people don't realize. Making fuel on Mars requires a lot of energy. You'd need a nuclear reactor or a massive solar array. Solar panels on Mars receive less than half the sunlight they get on Earth. Because Mars is farther from the sun, dust storms can cover your panels for weeks or months. A nuclear reactor solves the power problem, but now you're bringing a nuclear reactor to Mars, which adds mass, complexity, and risk. If something goes wrong with the reactor, you can't just evacuate. You're stuck there breathing radioactive dust. Number 14. The food problem is more complex than just bringing enough calories. You'd need roughly 2.7 kilograms of food per person per day. For a crew of 6 on a 2.5-year mission, that's about 15,000 kilograms of food. That's 15 tons. The ISS gets resupply missions every few months. Mars won't. You'd need to bring every meal for every day of the mission, plus extra in case something goes wrong, plus extra in case the return window gets delayed. Freeze-dried food keeps for years, but it's not nutritionally complete. Astronauts on the ISS lose bone mass and muscle mass despite eating a carefully designed diet. The food just doesn't provide everything the human body needs in zero gravity. Fresh fruits and vegetables provide micronutrients and phytochemicals that we don't fully understand, but that appear to be necessary for long-term health. You can't bring fresh food to Mars. It would spoil. You could try to grow food on the spacecraft or on Mars. NASA has experimented with growing lettuce and radishes on the ISS. It works, but it requires a lot of resources: water, light, temperature control, nutrient solutions. It's labor-intensive. Someone has to tend the plants every day, and the yield is tiny compared to what you'd need to feed a crew. To grow enough food for 6 people, you'd need a greenhouse the size of a football field. You don't have that kind of space on a spacecraft or in a Mars habitat. Even if you did, growing food in Martian regolith is a nightmare. The soil is toxic. It contains perchlorates, which are salts that destroy your thyroid if you ingest them. You'd need to wash the regolith extensively or bring your own soil from Earth. Bringing soil adds mass. Every kilogram of soil is a kilogram you're not using for something else. And plants need gravity. We don't know how plants grow in Martian gravity. Some experiments on the ISS have shown that plants get confused in microgravity. Their roots don't know which way to grow. Their stems bend in random directions. Mars has some gravity, 38% of Earth's, but we don't know if that's enough for normal plant growth. We'd have to test it, and the only way to test it is to go to Mars, which is the thing we're trying to figure out if we can do. The caloric density of food is another issue. You need about 2,000 to 2,500 calories per day, depending on your activity level. Astronauts on the ISS burn slightly fewer calories than they do on Earth, because they're not fighting gravity, but they still need adequate nutrition to prevent muscle and bone loss. Freeze-dried food is light but bulky. You can only compress it so much. The volume of food storage for a 2.5-year mission would take up a significant portion of the habitat, and food loses nutritional value over time even when freeze-dried. Vitamins degrade. Fats go rancid. By the end of the mission, you'd be eating food that's been stored for 3 years. It wouldn't kill you, but it wouldn't be optimal nutrition either. Number 13. The water situation on a Mars mission is just as bad as the food situation. You need water for drinking, cooking, hygiene, and growing food if you're trying to do that. A human needs about 3 to 4 liters of water per day just for drinking and food preparation. That doesn't include water for bathing, laundry, or growing plants. For a crew of 6, over 2.5 years, you'd need at least 20,000 liters of water just for drinking and cooking. 20,000 liters of water weighs 20,000 kilograms, or 20 tons. That's in addition to the 15 tons of food. You can recycle water to some extent. The ISS recycles about 93% of its water, including urine and humidity from the air, but that 7% loss adds up over a multi-year mission. You'd need to bring extra water to make up for the losses, and you'd need the equipment to recycle the water, which adds mass and complexity. The recycling systems on the ISS break down regularly. They require maintenance and spare parts. On Mars, if your water recycling system fails, you're in serious trouble. You can't just drink less water. Dehydration kills you in days. You'd need redundant water recycling systems, which means more mass, more complexity, more things that can break. Some people suggest mining ice on Mars to get water. Mars has water ice at the poles, and possibly buried under the surface in other regions. Mining ice on Mars requires heavy equipment. You need drills, heaters to melt the ice, pumps to move the water, and purification systems because Martian ice is probably full of perchlorates and other contaminants. All of this equipment adds mass to the mission. All of it requires power to operate. All of it can break, and you'd need to start mining ice as soon as you arrived on Mars to build up a water supply for the return trip. If the ice isn't where you thought it was, if it's deeper than expected, if the equipment breaks, you're stuck. Number 12. The launch windows for Mars missions are a hard constraint that people don't appreciate. Earth and Mars orbit the Sun at different speeds. The most efficient time to launch a mission from Earth to Mars happens once every 26 months, when the planets are properly aligned. This is called a Hohmann transfer orbit. If you miss the launch window, you have to wait another 26 months. That might not sound like a big deal until you think about what it means operationally. Imagine you've spent billions of dollars preparing for a mission. The crew has been training for years. The spacecraft is ready. Then 2 weeks before launch, a critical component fails. A fuel tank develops a crack. An engine test goes wrong. A crew member gets sick. Do you scrub the mission and wait 26 months? Do you rush the repair and hope nothing else goes wrong? Every delay costs money and increases risk because the crew is aging, the hardware is aging, and political support for the mission might evaporate. And once you're on Mars, you're stuck there for a year and a half waiting for the next return window. You can't just leave whenever you want. If someone has a medical emergency, if the habitat springs a leak, if you simply run out of something critical, you can't come home early. You have to wait. The return trip is another 7 months. So you're looking at a minimum mission duration of about 2.5 years from launch to landing back on Earth. There's no fast option. There's no abort to Earth button. Some people have proposed using nuclear rockets to shorten the transit time. Nuclear thermal rockets could potentially cut the trip to Mars down to 3 or 4 months instead of 7. That would reduce radiation exposure and the time spent in zero gravity. But nuclear rockets have their own problems. You're launching a nuclear reactor into space. If the rocket explodes during launch, you've just scattered radioactive material across a wide area. The political and environmental pushback would be enormous. No nuclear rocket has ever flown in space. The technology is decades away from being ready. And even if you had a nuclear rocket, you'd still be stuck on Mars for a year and a half because the orbital mechanics don't change. The planets still have to align for the return trip. Number 11. The landing on Mars is one of the most terrifying parts of the mission. Mars has enough atmosphere to create friction and heat during entry, but not enough atmosphere to slow you down effectively with parachutes. This is called the entry, descent, and landing problem, and it's killed more Mars missions than any other single cause. About half of all missions to Mars have failed. Most of those failures happened during landing. The atmosphere on Mars is 1% as thick as Earth's. On Earth, you can use parachutes to slow down a spacecraft to a safe landing speed. On Mars, parachutes help, but they're not enough. The Curiosity rover, which weighed about 900 kilograms, used a combination of a heat shield, parachutes, and a rocket-powered sky crane to land. It worked, but it was described by the engineers as 7 minutes of terror. Every step had to work perfectly or the rover would crash. Now imagine landing something much bigger. A human-rated Mars lander would weigh tens of tons. You'd need much larger parachutes, much more rocket fuel, and much more precision. You're landing on a planet where the weather is unpredictable. Dust storms can cover half the planet and last for months. Wind speeds can reach 60 miles per hour. Which doesn't sound that bad until you remember that the thin atmosphere means the wind has less force, but it's enough to blow dust around and reduce visibility to zero. If you're landing during a dust storm, you're landing blind. The surface of Mars is rough. It's covered in rocks, craters, and slopes. The rovers have all landed in carefully selected flat areas that were studied for years before the landing. Even then, Curiosity landed within 2 kilometers of its target, which is considered incredibly accurate. But 2 kilometers is a huge margin of error when you're trying to land next to a pre-positioned habitat. And supplies, if you land too far away, you can't walk to the habitat because you don't have enough oxygen in your spacesuit. If you land on a slope or a boulder field, your lander could tip over. The landing has to be perfect every single time. There's no second chance. You can't go around and try again. You get one shot. If anything goes wrong, the crew dies. And you need to land multiple missions at the same site. You'd need to send cargo missions first to deliver the habitat, the rovers, the ISRU equipment, the supplies. Then you'd send the crew. If any of the cargo missions fails to land in the right spot, the whole mission is compromised. Number 10. The dust on Mars is a bigger problem than most people realize. Martian dust is everywhere. It's fine, like talcum powder, and it's electrically charged because of the low humidity and the UV radiation. It sticks to everything. The rovers on Mars have all had problems with dust covering their solar panels. The Opportunity rover died because a dust storm covered its panels, and it ran out of power. The dust gets into seals, into joints, into electronics. It's abrasive, like tiny shards of glass, because it's never been worn smooth by water or whined the way sand on Earth has been. Martian dust is also toxic. It contains perchlorates, which I mentioned earlier, and possibly other chemicals that we don't fully understand. If astronauts track dust into the habitat on their spacesuits, which they inevitably will, everyone inside will be breathing it. The dust will get into the air filtration system. It'll get into the food. It'll get into the water. Long-term exposure to Martian dust could cause lung damage similar to silicosis, a disease miners get from breathing silica dust. Your lungs fill with scar tissue. You can't breathe. There's no cure. We could design airlocks with brushes and vacuum systems to try to clean the dust off spacesuits before astronauts come inside, but it won't be perfect. Some dust will always get through. And here's something most people don't think about. Static electricity on Mars is intense because of the dry, thin atmosphere. When you brush dust off your spacesuit, the static discharge could damage electronics. It could even ignite flammable materials if you're not careful. Astronauts on the moon dealt with dust problems, and the moon dust was also sharp and abrasive. But lunar dust doesn't have perchlorates. Lunar dust doesn't stick to everything because of static electricity in quite the same way. Martian dust is worse. Every time you go outside, you'd bring dust back in. Over time, the interior of the habitat would become contaminated. The air filtration systems would get clogged. You'd need to replace filters constantly, which means bringing spare filters, which adds mass. And if you run out of filters, you're breathing toxic dust until you die. Number 9. The thermal control problem on Mars doesn't get talked about enough. Mars is cold. The average temperature is minus 63 degrees Celsius. At nights, it can drop to minus 125 degrees Celsius at the poles. During the day at the equator, it might get up to 20 degrees Celsius. But that's the surface temperature. The air temperature is much colder. Your habitat would need heating to keep the crew alive. That requires a lot of energy. You'd need a nuclear reactor or massive solar arrays. And as I mentioned earlier, solar power on Mars is much less efficient than on Earth. Dust storms can reduce solar power to nearly zero for weeks. You'd need batteries to store energy for nighttime and dust storms, which adds mass and complexity. But it's not just about keeping warm. Spacecraft and habitats also have to deal with heat. Electronics generate heat. Humans generate heat. In space, you can't get rid of heat by convection because there's no air. You have to use radiators. On Mars, the thin atmosphere doesn't conduct heat well, so radiators are still necessary. If your thermal control system fails in space, you cook. If it fails on Mars, you freeze or cook depending on what breaks. The temperature swings on Mars are extreme. From day to night, the temperature can change by 100 degrees Celsius. Materials expand and contract with temperature changes. Over time, this causes stress fractures. Seals fail. Joints crack. The habitat would need to be designed to withstand these temperature swings for years. We don't have great data on how materials behave under Martian conditions over long periods. The rovers have given us some information, but they're not pressurized habitats with humans inside. They don't have the same requirements. A small crack in a habitat on Mars could be catastrophic. The internal pressure would force air out through the crack. You'd have hours, maybe days, to find and patch it before you ran out of air. And patching a crack in a habitat that's being heated and cooled by 100 degrees every day is not as simple as slapping duct tape on it. Number 8. The communication delay with Earth makes real-time decision-making impossible. At its closest, Mars is about 54 million kilometers from Earth. At its farthest, it's about 400 million kilometers away. Light, which is the fastest thing in the universe, takes between 3 and 22 minutes to travel from Earth to Mars, depending on where the planets are. That means, if you send a message to Earth, it takes up to 22 minutes to get there, and the response takes another 22 minutes to get back to you. That's a 44-minute round trip. You can't have a conversation. You can't ask mission control for help in an emergency. If something breaks, you're on your own. The crew has to make every decision without input from Earth. This is completely different from every other human spaceflight mission. The Apollo astronauts had a 2.5-second communication delay, which was short enough for real-time conversations. ISS astronauts have essentially no delay. They can call mission control anytime. Mars astronauts would be truly isolated. Psychological impact of this is hard to overstate. You can't call home when you're homesick. You can't get advice from experts on Earth when something goes wrong. You have to rely entirely on on the knowledge and skills of the 6 people in your crew, and those 6 people have to get along for 2.5 years with no outside support. The communication delay also affects scientific research. If you find something interesting on Mars, you can't immediately share your data with scientists on Earth and get their input. By the time they respond, you might have moved on to a different site. The whole mission would move at a glacial pace compared to what we're used to. Every decision would take hours or days instead of minutes. Some people suggest using AI to help the crew make decisions, but AI isn't magic. It's only as good as the data it's trained on, and we don't have comprehensive data on everything that could go wrong on Mars. An AI might give you a suggestion, but you'd still be making the final call with no way to verify if you're right until it's too late. Number 7. The medical care problem is unsolvable with current technology. If someone gets sick or injured on Mars, you're limited to whatever medical supplies and expertise you brought with you. You can't evacuate them to a hospital. You can't call in a specialist. The crew would need to include someone with extensive medical training, ideally a surgeon, but even a highly trained doctor can't perform every procedure. If someone needs a CT scan, you don't have a CT machine because it's too heavy. If someone needs blood, you'd better hope another crew member has a compatible blood type. If someone gets appendicitis, which is not uncommon, you'd need to perform an appendectomy in a makeshift operating room with improvised equipment. People have done surgery in Antarctica research stations, so we know it's possible, but those stations have more resources than you'd have on Mars. Can call in an air evacuation if things go really wrong. Mars doesn't have that option. Radiation exposure increases cancer risk, but cancer takes years to develop. You might not know someone has cancer until you're already on Mars. If they do, there's no chemotherapy. There's no radiation therapy. You'd just have to watch them die. Kidney stones are another concern. They're more common in space because of the way calcium is processed in zero gravity and dehydration. Kidney stones are excruciatingly painful. If one gets stuck, it can block urine flow and cause a medical emergency. On Earth, doctors can use lithotripsy, a procedure that uses sound waves to break up the stone. On Mars, you'd have to pass the stone naturally or perform surgery. Dental emergencies are another nightmare. If someone gets a severe toothache, you'd need to pull the tooth or perform a root canal with hand tools and local anesthetic. Infections are a constant risk. A simple cut that gets infected could turn into sepsis if you don't have the right antibiotics. Bacteria evolve. They develop resistance to antibiotics, and in the closed environment of a spacecraft or habitat, antibiotic-resistant bacteria could spread quickly. If someone develops a resistant infection, they could die because you don't have the drugs to treat them. The mental health issue compounds the medical problem. If someone becomes severely depressed or psychotic, you might need to sedate them or restrain them. You don't have a psychiatrist on crew. You don't have a mental health ward. You just have a small habitat with nowhere to isolate someone who's a danger to themselves or others. Number 6. The return trip from Mars is just as dangerous as the outbound trip, maybe more so. You'd have been on Mars for a year and a half, living in reduced gravity, being exposed to radiation, eating stored food that's been sitting for years. Your body would be in worse shape than when you left Earth. Your bones would be weaker. Your muscles would be smaller. Your cardiovascular system would be deconditioned. Now you have to get back into a spacecraft, spend another 7 months in zero gravity, and then survive re-entry into Earth's atmosphere. The G-forces during re-entry are brutal. Apollo astronauts experienced up to 6 Gs during re-entry. After spending 2.5 years in space and reduced gravity, 6 Gs might be enough to cause you to black out, or have a heart attack. Your weakened bones might fracture under the load. If you black out during re-entry, you can't pilot the spacecraft. Everything would have to be automated, and automation can fail. Before you even get to re-entry, you have to launch from Mars. That means the ISRU equipment you sent ahead has to work perfectly for a year and a half, producing enough methane and oxygen to fuel the return vehicle. If it doesn't, you're stuck on Mars. There's no backup. Some people have proposed sending multiple return vehicles to Mars as redundancy, but that multiplies the cost and complexity. You'd need to land multiple spacecraft at the same site, all of them functioning perfectly after sitting on Mars for a year and a half in dust storms and temperature swings. The Martian environment is harsh. Seals degrade. Lubricants freeze. Electronics fail. The return vehicle would need to be robust enough to survive 18 months of exposure and then launch flawlessly. We've never tested that. We've never left a fueled rocket on Mars for 18 months and then tried to launch it. Don't know if it would work. And if the launch from Mars fails, if the rocket explodes on the pad or crashes shortly after liftoff, the crew dies. There's no abort system that can save them. They're too far from Earth for a rescue mission. They'd just be stuck on Mars waiting for their supplies to run out. The orbital mechanics of leaving Mars are also unforgiving. You need to launch at precisely the right time to intercept Earth's orbit months later. Miss that window by even a small margin, and you could end up on a trajectory that misses Earth entirely, sending you into a solar orbit from which there's no recovery. The navigation has to be perfect. The rocket has to perform exactly as designed. Any deviation, and you're dead. Then there's the question of what happens to the spacecraft during the return journey. It's been through 7 months of space, 18 months on Mars exposed to dust and temperature extremes, and now it has to function flawlessly for another 7 months. The life support system has to keep working. The radiation shielding, whatever minimal shielding you have, has to hold up. The communication system has to function so you can talk to Earth, even with the delay. The propulsion system has to make course corrections. Every system is older, more worn, more likely to fail than it was on the outbound journey. By the time you're approaching Earth, these systems will have been operating for over 2.5 years. That's longer than most satellites are designed to last. Satellites don't have to keep humans alive. The re-entry itself is the final gauntlet. You're hitting Earth's atmosphere at 11 kilometers per second. The heat shield has to protect you from temperatures exceeding 2,000 degrees Celsius. If there's any damage to the heat shield, from micrometeorites or material degradation, you burn up. The parachutes have to deploy at exactly the right altitude and speed. If they deploy too early, they'll rip apart. Too late, and you'll hit the ground at terminal velocity. Everything has to work perfectly after 2.5 years in space. And even if you survive re-entry and landing, you're not done. Your body has been in space for all that time. When you try to stand up on Earth, your heart might not be able to pump blood to your brain. Your legs might not support your weight. You might need to be carried out of the capsule on a stretcher. Astronauts returning from 6-month ISS missions need weeks to regain the ability to walk normally. After a Mars mission, you'd need months or years of physical therapy. Some of the damage might be permanent. You might never fully recover. Number 5. The spacecraft itself is a single point of failure with thousands of components that all have to work perfectly. We're not talking about a car where if something breaks, you pull over and call a tow truck. We're talking about a complex machine hurtling through the vacuum of space, where any major failure means everyone dies. The life support system has to scrub carbon dioxide from the air continuously. If it fails, you have hours before CO2 levels become toxic. The thermal control system has to keep temperatures stable. If it fails, you cook or freeze. The power system has to provide electricity for everything. If it fails, you're in the dark with no heat, no air circulation, no water recycling, no communication. Every system has backups, but backups can fail too. The more complex the system, the more ways it can break. And you can't bring spare parts for everything. You'd need to bring spares for the most critical components, but that adds mass. Engineers have to make decisions about what's worth bringing a spare for, and what isn't. If they guess wrong, people die. The spacecraft would need to be assembled and tested on Earth, then launched into space, possibly in pieces that get assembled in orbit. Every connection point is a potential failure point. Every weld could have a microscopic flaw. Every seal could degrade over time. We've had decades of experience with the ISS, and it still has failures. Pumps break, cooling systems malfunction, air leaks develop. The difference is, the ISS can be resupplied and repaired. Astronauts can do spacewalks to fix external problems. If something catastrophic happens, the crew can evacuate in a Soyuz capsule and be back on Earth in 3 hours. Mars spacecraft has none of those options. If something breaks that the crew can't fix with the tools and parts on board, the mission is over. And here's what really keeps engineers up at night. Unknowns. We don't know what we don't know. There could be failure modes that we haven't even thought of. Materials behave differently after years in space. Radiation damages things in ways we don't fully understand. The spacecraft would be operating beyond any environment we've ever tested for extended periods. Apollo missions lasted days. ISS missions last months. A Mars mission is years. That's an entirely different category of risk. Number 4. The cost of a Mars mission is so astronomical that it's difficult to justify when we have pressing problems on Earth. Estimates vary, but most serious analyses put the cost of a first Mars mission somewhere between $100 billion and $500 billion. NASA's entire annual budget is around $25 billion. A Mars mission would consume multiple years of NASA's entire budget, and that's assuming everything goes according to plan, which it never does. The James Webb Space Telescope was supposed to cost $1 billion and take 10 years to build. It ended up costing $10 billion and took 25 years. Massive engineering projects always go over budget, and over schedule. A Mars mission would be orders of magnitude more complex than the Webb telescope. The real cost could easily exceed $1 trillion when you factor in all the technology development, testing, infrastructure, and the inevitable delays and redesigns. For that money, we could solve malaria. We could provide clean water to everyone on Earth. We could build thousands of schools and hospitals. We could fund decades of climate change mitigation. The argument for going to Mars is usually framed as advancing human knowledge and ensuring the survival of our species, but there are much cheaper ways to do both. We can learn about Mars by sending robots. The rovers have been incredibly successful, and they cost a tiny fraction of what a human mission would cost. If we're worried about human extinction, we'd be better off spending that money on preventing asteroid impacts, mitigating climate change, preparing for pandemics, or developing sustainable energy. A Mars colony wouldn't save humanity anyway. It would be completely dependent on Earth for decades or centuries. If something catastrophic happened on Earth, the Mars colony would die shortly after. They couldn't survive without regular supply missions. The political reality is even worse. A Mars mission would require sustained funding over multiple presidential administrations. The moment the political winds shift, the funding gets cut. We've seen this happen over and over. The space shuttle was supposed to fly dozens of times per year and make space access routine and cheap. It ended up being incredibly expensive and dangerous, and the program was canceled. The Constellation program was supposed to return humans to the moon. It was canceled. The same thing could easily happen to a Mars program after billions have already been spent. Number 3. The ethical problem of sending people on a suicide mission is something we need to confront honestly. Let's be clear about what a first Mars mission really is. It's sending 6 people on a 2.5-year journey with a very high probability that at least some of them will die. Maybe they all die. The radiation alone significantly increases their cancer risk for the rest of their lives. The bone density loss might never fully recover. The vision problems might be permanent. The cognitive damage from radiation might be irreversible. Even if everything goes perfectly and they make it back to Earth alive, they'll have sacrificed their health. They'll spend the rest of their lives dealing with the consequences. Is it ethical to ask people to do that? Some would argue that if people volunteer knowing the risks, that's their choice. We let people climb Mount Everest even though some of them die. We let people become test pilots and deep-sea divers, do other dangerous things. But there's a difference. Those activities serve a purpose beyond the activity itself. Test pilots help develop safer aircraft. Deep-sea divers do research and repair underwater infrastructure. What does the first Mars mission accomplish that's worth the human cost? We'd learn some things about Mars that we couldn't learn from robots. Would we learn enough to justify the deaths? And what about the people who don't volunteer, but who would be affected? The crew members have families. If an astronaut dies on Mars, their children grow up without a parent. Their spouse becomes a widow. Their parents outlive their child. Those people didn't volunteer for anything. They're just collateral damage in humanity's quest to plant a flag on another planet. There's also the problem of informed consent. Can someone truly give informed consent to a mission when we don't fully understand all the risks? The radiation effects on the brain might be worse than we think. The psychological effects might be worse than we think. We won't know until we try, and by then, it's too late for the crew. Some space advocates talk about Mars missions as if the risks are acceptable, because exploration has always been dangerous. They compare it to the Age of Sail, when explorers set out on ships, and many never came back. But that comparison is flawed. Those historical explorers had a reasonable expectation of success. Many voyages did succeed. Ships made it to the New World and back. A first Mars mission has no such track record. We'd be sending people into an environment where we know some of the risks are severe, and where there are certainly other risks we don't even know about yet. Number 2. The micrometeorite problem is something that doesn't get enough attention. Space is not empty. It's full of debris. Tiny particles, some no bigger than a grain of sand, are traveling at tens of thousands of kilometers per hour. When one of these particles hits a spacecraft, it hits with enormous energy. The ISS has been hit thousands of times by micrometeorites and space debris. The windows have to be replaced regularly because they get pitted and cracked. The solar panels degrade over time from impacts. The station has Whipple shields, which are layers of material designed to break up incoming particles before they can penetrate the hull. Even with those shields, impacts happen. A particle smaller than a centimeter could punch through the hull of a habitat module and cause explosive decompression. The crew would have seconds to get into their spacesuits, or seal off the affected section. Between Earth and Mars, you'd be exposed to the micrometeorite environment for 7 months on the way out, and 7 months on the way back. The probability of a catastrophic impact increases with time. The spacecraft would need extensive shielding, but shielding adds mass. And every kilogram of shielding is a kilogram you're not using for food, water, or fuel. Engineers have to make trade-offs. How much protection is enough? How much can you afford in terms of mass budget? There's no perfect answer. On Mars, you'd be somewhat protected by the atmosphere. It's thin, but it's enough to burn up most small particles before they reach the surface. But you're not safe. Larger meteorites still make it through. Mars has been hit many times throughout its history. The probability of a meteorite strike during your 18 months on the surface is low, but it's not zero. If a meteorite hits your habitat, you're done. There's no emergency shelter you can run to. You're living in the only pressurized environment on the entire planet. The psychological effect of knowing you could be killed at any moment by a random piece of rock traveling at orbital velocity would be immense. You couldn't do anything about it. You couldn't see it coming. You just have to hope your luck holds out for the entire mission. Number 1. The fundamental problem is that Mars is not a backup planet for humanity. This is the thing that people need to understand. Even if we solved every single technical challenge I've described, even if we could send people to Mars and bring them back safely, even if we could establish a permanent settlement, Mars would not be a self-sustaining backup for human civilization. The idea that we need to become a multi-planetary species to survive is based on a flawed premise. The premise is that Earth might become uninhabitable, and we need somewhere else to go. But think about what would make Earth uninhabitable. Climate change, nuclear war, a pandemic, an asteroid impact. Even in the worst case scenarios, Earth would still be more habitable than Mars. After a nuclear war, Earth would have breathable air, drinkable water, edible plants, and liquid water on the surface. Mars has none of those things and never will. You can't terraform Mars. The planet doesn't have enough atmospheric pressure. It doesn't have a magnetic field to protect a thicker atmosphere even if you could create one. Any atmosphere you added would be stripped away by solar wind over geological time. You could build underground habitats on Mars, but you could also build underground habitats on Earth if things got bad. It would be easier and cheaper to build them on Earth because you wouldn't need to transport everything to another planet first. The resources you'd spend making Mars marginally habitable for a small number of people could be spent making Earth more resilient for billions of people. A Mars colony would be dependent on Earth for everything for the foreseeable future. They'd need supply missions to bring equipment, spare parts, electronics, specialized materials, possibly food. If Earth suffered a catastrophe that destroyed our industrial civilization, those supply missions would stop, and the Mars colony would die. They couldn't manufacture computer chips. They couldn't produce the medical equipment they'd need. They couldn't maintain the complex systems required to keep people alive in such a hostile environment. The romantic notion of Mars as humanity's backup is just that. A romantic notion. It doesn't hold up to scrutiny. If we're serious about ensuring humanity's long-term survival, we need to focus on making Earth sustainable. We need to address climate change, develop better pandemic preparedness, track and deflect dangerous asteroids, reduce the risk of nuclear war. Those are the real threats to human survival, and they're all solvable with technology and political will. That's far more achievable than a self-sustaining Mars colony. Mars is interesting scientifically. Sending robots to study it makes sense, but sending humans there is a vanity project. It's something we want to do because it seems bold and ambitious, not because it serves a practical purpose. And the cost, both in money and in human lives, is far too high for what amounts to planting a flag and saying, "We did it." That's the reality nobody wants to talk about.